Hello, so today we'll discuss commutators in quantum mechanics. So this is a plan of this talk. First we will talk about what is quantum mechanics, then we will talk about operators and observables also, then we will derive commutation relation, and then we will link commutation relation with uncertainty principle. So quantum mechanics is a fundamental theory of physics describing physical properties of nature at atomic and subatomic scales. And in quantum mechanics, there is a principle of wave-particle duality. It says that microscopic particles, such as electrons, protons, and photons, can exhibit both wave-like and particle-like properties. And the probabilistic nature quantum mechanics gives us probabilities for the outcomes of measurements. It's a theory at the microscopic level, and this theory provides outcomes of a measurement. And it is not a deterministic theory. It is a theory which is probabilistic. Quantum mechanics also has the machinery of predicting outcomes of real experiments which are at the macroscopic scale. And quantum mechanics also has a mechanism for predicting the outcomes of measurement in the microscopic level. So quantum mechanics revolutionized our understanding of the microscopic world, explaining the phenomena that classical physics could not. It provides a framework for understanding the behavior of electrons, photons, and fundamental particles. Quantum mechanics is essential for understanding of condensed matter physics, nuclear physics, particle physics. Quantum mechanics has led to many technological advancements such as semiconductors, laser, quantum computing. Quantum mechanics has also given us philosophical insights of reality, causality, physics of early universe, and practical applications also, such as in medicine, electronics, and cryptography. So what are operators? In quantum mechanics, operators represent physical quantities in the form of this eigenvalue equation. Here the psi, the wave function, represents a quantum state. O is operator, lambda is eigenvalue, and this is again the quantum state, or it's a wave function. The wave function represents a quantum state, and the operator represents an observable, and the eigenvalue represents outcomes of measurements at the quantum level. And these eigenvalue equations have their origin in the works of Joseph Fourier and David Hilbert. Fourier and Hilbert studied eigenvalue equations. Fourier studied in the form of heat conduction, and David Hilbert, he studied eigenvalues equations in the context of pure mathematics. Now, what is Schrödinger equation? Schrödinger equation describes how quantum state of physical system changes over time. So this is a differential equation. And what is a wave function? Wave function is the solution of the Schrödinger equation, which represents the quantum state of a particle. The Schrödinger equation governs the evolution of quantum systems. Solving it provides the wave function, which is used to calculate probabilities and physical observables in quantum mechanics. And what is commutator? Commutator between two operators A and B is represented as AB minus BA. A and B are two operators. And what is its physical significance? Commutators reveal whether two physical quantities can be simultaneously measured with precision. Non-zero commutators indicate that there is a fundamental limit to the precision with which certain pairs of properties can be known at the same time. So xp equal to IH cross, this is also sometimes called the equal time commutator. Next, let us talk about the derivation of a commutator. So first, let us multiply x and p, xp in this order, and later we will multiply in this order, px. So when we multiply in this order xp, then first we have to apply p, so minus ih cross d dx ix, and then we have to apply x. Then we get x minus ih cross d dx ix. Here x is not an operator, this is just variable, but here it's operator. So when x operator acts on a function, any function psi, it just multiplies that function with x. And apply operators in reverse order, px. Then first we have to multiply psi with x because x operator, and then after that we have to take the derivative, this derivative psi x psi. So it gives x d psi dx plus psi x. And when we subtract, then this term gets cancelled. We get ih cross psi. Let's get ih cross psi. So this is the property of the derivative. So because when we take the derivative of the product of two functions x and psi, then we get an extra term, which is the second term, and this doesn't get cancelled. The first term gets cancelled with this, but the second term doesn't get cancelled. So it gives a non-zero commutator in the right hand side. This is very fundamental in the quantum mechanics. How it is very fundamental? So let us apply the generalized uncertainty relation sigma a sigma b greater than or equal to half magnitude of the expectation value of the commutator a and b. So a and b commutator, if we put it, is just ih cross. So expectation value is ih cross and its magnitude is h cross. So we get delta x delta p greater than or equal to h bar by 2. That means the commutator which we have obtained here is linked with the uncertainty principle. Delta x delta p greater than h bar by 2. So this principle implies that increasing the precision in measuring one quantity leads to the increased uncertainty in measuring the other, and it reflects the wave-particle duality and probabilistic nature in quantum mechanics. The commutator between position and momentum is not the only commutator in quantum mechanics. There exists other operators having such non-trivial commutation relations. For example, we have already discussed the commutation relations between Lx, Ly, Lz, angular momentum commutation relations. And we have seen that they form an algebra, operator algebra, an area of theoretical physics dealing with mathematical structure and properties of operators. And this operator algebra is needed to study symmetries, conservation laws. Symmetries and conservation laws at the microscopic level, and they provide the basis for understanding complex physical systems at the microscopic scales. And then some references. There are old references, Heisenberg and Dirac, and modern references, Sakurai and Napolitano, and Griffith and Schroeter. And I will give this PDF in the description box so that you can look at these references and also the derivations that I have given today. So thank you for watching.